It's my pleasure to introduce the next presenter, Marie Trenkel, who's a pharmacist and PhD student at Kiel University. Her project focuses on nasal powder formulations and investigating different influences of excipients in the nose. Her research interests include investigation of occurring sensory effects and the characterization of the influence of excipients on systemic drug absorption. Take it away.
Yeah, thank you for the introduction, and thank you also for the possibility to speak today as part of the Pat Bernal Young Investigator Award. And hello, everyone. As we've already heard, I'm working on the characterization of different influences that excipients may have in nasal powder formulations. And today I'm happy to present one part of the research to you that I've conducted in the last years as PhD student at Kiel University. And the focus of today's talk is on the characterization of influences that excipients may have on the absorption of a drug. The nose offers us different possibilities for drug delivery, and one of them is the easy access to a relatively permeable mucosa, and with that, the possibility for systemic drug delivery. But the nose also poses very specific challenges, and one of the most striking there is the short residence time of drugs due to the mucociliary clearance. And if the specific challenges of the nose are not addressed during product development, that can cause the failure of the developed product. Formulations can be a key to overcome these challenges, and one strategy is to use nasal powders with excipients like fillers, mucoadhesives, or permeation enhancers. Excipients may influence different processes on the way to drug absorption, and the challenge we initially wanted to target is mucociliary clearance, and excipients can affect this process, but they will also affect further processes like the dissolution and the permeation of a drug. And the research questions we wanted to answer are therefore, how can we differentiate between the different influences that excipients may have on drug absorption from powder formulations, and how can we translate this knowledge then into successful nasal products? To answer these questions, I prepared different model formulations with atenolol as model drug, which shows low and paracellular permeation and is slightly soluble in a simulated nasal fluid. And I blended atenolol with mannitol or microcrystalline cellulose as soluble or insoluble fillers, and with pectine, chitosan glutamate, or HPC as mucoadhesives, which showed promising results on previous studies. On the next slides, formulations that contain the soluble filler mannitol will be shown in blue, and formulations with the insoluble filler MCC will be shown in green. The first question I want to address today is how can these formulations affect the mucociliary clearance? The nasal clearance is influenced by the viscoelasticity of the nasal mucus, and studies found that the elasticity is especially important, and optimal clearance rates were obtained with an elastic moduli of 1 to 2 Pascal. And based on that, I conducted oscillatory rheological measurements which enable the differentiation of the elastic and viscous part of a viscoelastic sample. For sample preparation, I dispersed 1 dose of the formulations into an estimated initial nasal fluid volume of a simulated nasal salt solution. This graph shows the elastic and viscous moduli of the different samples, and what we can see is that the pure drug, so only atenolol, already reached an elastic modulus of about 12 Pascal, which could be sufficient to decrease the nasal clearance rate. And this increase in elasticity was due to undissolved drug particles. So the undissolved drug itself may already prolong the nasal residence time. However, this effect would decrease with progressing dissolution of the drug in the nose, so insoluble excipients or mucoadhesive excipients may still be beneficial and induce a longer lasting effect. An additional effect, so further increase in the elastic and viscous moduli, was only observed with the formulations that contain the insoluble filler MCC and HPC as mucoadhesive in the study. Formulating a drug with insoluble or swelling excipients will not only influence its nasal residence time, but also its dissolution behavior in the nasal cavity. And to assess this, I used the Franz cell setups. Franz cells allow the separation of a donor compartment and an acceptor compartment, and the powder can then be placed on a wetted membrane in between. So we can assess the dissolution of the drug only on a wet surface as it would be in the nasal cavity. And in this setup, the membrane should only provide a physical separation of the powder from the acceptor medium, but should not provide a permeability barrier, since I only wanted to assess the dissolution in this setup. This graph shows the dissolution of the formulations related to the dissolution of pure atenolol, which is shown as 100% in this graphic. And what we can see is that the formulations that contain the soluble filler, mannitol, with or without chitosan glutamate, showed a similar dissolution profile to the pure drug, while all the other formulations that contain either insoluble excipients or higher viscous excipients decreased the dissolution rate, and the dissolution profiles there were similar to each other. When we remember the results from the rheological assessment, we can assume that the formulations that contain the insoluble filler MCC and HPC as mucoadhesive may be especially beneficial if a long nasal residence time is required for drug permeation, since it provided the highest elastic and viscous moduli while decreasing the dissolution rate to a similar extent than the other formulations with insoluble or viscous excipients. And a decreased dissolution rate does not need to be disadvantageous, since, for example, if the permeability is the limiting factor for drug absorption, the undissolved powder or the drug which is embedded in a matrix out of the mucoadhesive may provide a higher resistance against the nasal clearance, and with that provide a longer time for drug permeation. So the permeability of the drug on the one hand influences which excipients or formulations are really beneficial. On the other hand, the excipients may also directly influence the permeation of the drug. And to assess this effect, I conducted permeability studies using the RPMI 2650 cell line. And since I wanted to distinguish the effect of the excipients on the dissolution and directly on the permeation, I used drug solutions with single excipients in this part of the study instead of applying the formulations as powders. This graph shows the permeability coefficients of the drug with or without the different mucoadhesives. And what we can see is that pectine and chitosan glutamate significantly reduce the permeability of atenolol. For chitosan glutamate, however, a permeation enhancing effect based on the opening of tight junctions is reported, so we would have expected just the opposite effect here. What we have seen is that the transepithelial electric resistance, which indicates the tightness of the cellular barrier, decreased after contact with chitosan glutamate. So that could support the mechanism of opening tight junctions, but the permeability was reduced, and we assume that may be due to the slightly acidic reaction of chitosan glutamate. Since atenolol is a weak base, a higher portion of the drug molecule might be in its ionized form, which then may contribute less to drug permeation. And the charged drug molecule may also interact with negatively charged group of the mucous layer, which covers the cell surface, which may provide a diffusion barrier. And also the positively charged chitosan may interact with negatively charged groups of the mucous layer, and an accumulation of the positive charge due to the chitosan molecules may also provide a further diffusion barrier for charged drug molecules. We will conduct further experiments on these effects to support these hypotheses. In general, we can say that the effect of excipients on the permeation may strongly depend on the properties of the drug, and in this case, the use of chitosan glutamate as permeation enhancer may be limited in nasal powder formulations with drugs that are weak bases, since pH adjustment would then be difficult in powders. How can we translate these experiments into successful nasal products? Powder formulations and the use of excipients offer the possibility to optimize drug absorption, but to do that successfully, we need a differentiated knowledge about the different effects that excipients may have on this process. And the methods described in this study can detect additive effects of excipients, but also counteracting effects of excipients. And with that, they enable the selection of substances and formulation candidates with the most promising overall properties. And which properties are really promising depends on the drug substance and its characteristics, like its dissolution behavior and its permeation behavior in the nose, and also its medical indications. So the drug needs to be the starting point for the selection of excipients. with these considerations, I want to finish for today. Thank you for your attention.
Does anyone have any questions?
Hi, thank you for the presentation. Snezhana, GSTA Antivirals. I was just thinking, because you mentioned you used cell lines. Have you thought about using primary cell lines from human volunteers? Because maybe you see the different impact of the excipients.
Yes,
Thanks.
we've thought about that, but the main aim was to provide a set of methods which is easy to use and applicable for screening of excipients and formulation candidates. So we wanted to choose methods that show us the highest possible reproducibility, and that's why we decided to use the cell line.
Start simple, then go more complex. Thanks.
Hi, yeah, really nice talk. I've got some questions about your rheology. So you measured the elastic and viscous moduli under oscillation. Did you take into consideration, I don't know, relevant frequencies, like cilia beat frequencies or anything like that when you did those measurements?
Yeah, we did that frequency dependent, and the values that was presented here were at an oscillatory frequency of 1 hertz, which was also which was selected because of the studies which I mentioned, which shown an optimal clearance rate with 1 to 2 Pascal, were also at this frequency.
Okay, cool thing. And did you measure these viscosity as well of these things under steady shear?
Yes, we also measured the viscosity. So we measured the viscosity alone, but also the viscous moduli. So I think the viscosity is also an important factor on the one hand for the clearance, but on the other hand also for the dissolution. It will definitely affect the dissolution or the diffusion of the drug through the matrix which may be built up.
That's great, thank you.
There's one more question.
Yeah, Carsten Ehr, Trinity College Dublin. Thanks, very nice presentation. I have a comment and 2 quick questions. So the comment is the RPMI 2650 cells don't have functional tight junction, so I would have been surprised if you saw a tight junction opening effect. How did you measure the tear values technically? Because you report values that are very kind of precise.
Yeah, I measured it with this voltometer.
Okay.
So in the chopstick electrode.
Okay, and then secondly, the pH. What is the physiological pH in the nasal fluid?
Yeah, in the nasal fluids, the pH would be slightly acidic, so about 6.4, I think. This pH here was adjusted to the cell experiments, but I think the acidic reaction will be of calcium glutamate will also be visible if it's dissolved in the slightly acidic nasal fluid.
Okay, thank you.
Any more questions? Okay. Thank you so much, Marie.